capacitance bridge. Basically, what this bridge is that it is a device that is used to measure the unknown inductive impedance L1 by comparing it with the standard capacitance C4. So this is the general schematic of this bridge. So like I said before, L1 is the unknown resistance of the inductor. R2, R3, R4, which is this resistance right here. This resistance and this resistance are the non-inductive resistance. C4 is a variable capacitance, which means that we can change this value of capacitor, and R1 is basically the effective resistance of this inductor here. So now moving on, basically there is something called balance condition. What this condition is that the effective resistance across this arm right here multiplied by the effective resistance across this arm is equals to the product of the effective resistance across this arm multiplied by this resistance across this arm, right? So basically that condition is represented by this equation right here. So Z1 is basically the resistance. Z1 times Z4 is equals to Z2 times Z3. Now what is Z1, right? But to figure out what is Z1. Z1 is basically the sum of resistance R1 and the resistance across this inductor right here. So R1 is just R1 itself, right? And the resistance L1 can be represented by J omega L1. So that's basically the effective resistance across this arm right here. Now to figure out the effective resistance across this arm, what we have to do is we have to define, as you can notice, C4 is trying to take parallel with the resistance R1, right? So we have to apply the parallel condition. So when we do that, what happens is that we have to multiply the value of R4 times the effective resistance of this capacitor right here, which is basically represented by 1 over J omega C4, divided by the sum of this resistance R4 plus J omega C4. So when we simplify this part right here, when we get this part right here, so what we're left is R4 divided by R4 J omega C4 plus 1. So this is the effective resistance across this arm right here. Now what I have to do is as you can already see, the resistance across this arm is basically this resistance R2, and the resistance across this arm is just basically the resistance R3, right? Now what we have to do is we have to substitute these two values and the value of these two resistors in the balance condition right here. So as you see, we have substituted R1. This is basically R1, and this is basically Z1. This is effective resistance across this arm is equals to R2 and R3, which is basically Z2 and Z3. Now what we have to do is we have to simplify this equation in order to get the value of L1 and the value of R1, which is basically the unknown variables, right? So now, as you can see, what we have to do is we have to multiply this component right here with these two terms right here. And when we do that, what we are left is this equation right here. So, as you can see, it's been multiplied individually into those two components. So, now what we have to do is we have to take this denominator, which is basically R4, J omega C4 plus 1 to the other side. So, as you can see, we have taken it to the other side. When we do that, R2 plus R3 is multiplied with 1, and then it's also multiplied with this value right here. So, what we are left is R2 plus R3 plus R2, R3, R4, J omega C4. Now, like I said before, we have to get values of the unknown resistance R1 and R1. So, what we have to do is we have to separate the imaginary part and the real part of this equation right here. So, everything that includes J omega is basically the imaginary part. So, now what we have to do is, as you can see, R1 and R4 is free of J omega. So, this is basically the real part, and R2 and R3 is the real part of this side of the equation. So, equating these two equations, what we have left is R1 times R4 equals R2 times R3. Now, value of the unknown resistance across R1. Now, this is the real part. Now moving on to the imaginary part. So this, like I said before, this is the imaginary part right here. J omega L1 R4, since it contains J omega, and the imaginary part of this side of the equation is R2, R3, R4 times J omega C4, right? So this is the imaginary part of this side of the equation. Equating these two components, what we have to do is we have to isolate the value of L1, since we're trying to figure out the value of L1, right? So what we're left with is L1 is equals to R2, R3 times C4, because when we equate these two, value of J omega and J omega gets cancelled, and R4 and R4 gets cancelled. So in the end, we're left with this L1, which is equals to R2, R3 and C4. So now we've gotten the values of the unknown inductance and the unknown resistance in terms of known components, which is basically the three resistors and the C4 component, right? Okay, now we're going to look at something called quality factor and dissipation factor of Maxwell's inductive. What is quality factor? Quality factor is basically the indication of how much energy is stored with respect to the energy dissipated in one cycle. So basically, the quality factor or the T factor is given by the equation omega L1 by R1. We already seen the formula for L1 and R1, right? We derived this. So what we have to do is we have to substitute the value of R1 and L1 in this quality factor equation. So when we do that, this is when we do the substitution. What we're left with is basically omega C4 by R4. So this is the quality factor of the bridge. Now the next thing we have to know is the dissipation factor. Dissipation factor is the indication of how much energy is dissipated with respect to the stored energy in one cycle. Basically, in other words, we can say that dissipation is the reciprocal of the quality factor of the factor. So when you substitute the value of Q, which is omega C4 by R4, what we're left with is 1 by omega C4 R4. So this is the dissipation factor. Okay, now what we're going to do is we're going to look at the phase diagram of this bridge right here. So, firstly, we have to consider the voltage across this arm right here. Voltage across this arm is represented by E1, right? E1 is basically the voltage across this resistor and voltage across this inductor. So, firstly, what we're going to do is we're going to write phasor I1 as a reference phasor, right? Here, I1 represented as a reference phasor I1. Okay, to where is I1, right? Now, like I said before, since the E1, basically E1 is the voltage across this component right here. The first component, voltage across the first component will be represented by I1 and R1, right? So basically that will be voltage across this resistor. So I1 and R1 is represented right here. Now the voltage across that inductor is basically leading the voltage of this resistance by a factor of 90 degrees. So that means the voltage across this inductor will be represented by this perpendicular phasor right here. This right here. This is I1 J omega L4. So that is the voltage across that inductor right here. Now the resultant of these two phasors will basically give us the effective, will basically give us the value of E1. So the resultant of these two phasors is basically this phasor right here. So this is basically E1. Now what we have to know is that at balanced condition, the value of E1 will be equal to the voltage across this arm right here, E2. So we can equate the value of E1 to the value of E2. So when that happens, what is E2? E2 is basically voltage across this arm right here, right? So in order to find E2, what we have to do is I have to multiply the current I2 flowing through this line with the value of resistance right here. So E2 is basically I2 and R2. So that means current I2 is in phase with this E1, right? So we can extend this line from here, and this is basically current I2. Now the current I2 can also be represented by we know that current I2 is equal to current I4, because as you can see here, as the current I2 flows through this junction right here, this arm, it will then move to this arm right here, right? So I4 is basically the sum of the current flowing through this capacitor and the sum of current flowing through this resistor. So as you can see, we can conclude that the current I2 is equal to I4 by these conditions. So that's why we have written here I2 is equal to I4. Now, in order to represent I2, we know that I2 is equal to I4, right? So I4 can be represented by the sum of these two currents, IC and IR. So we have IR basically in phase with this current right here. So therefore IR can be written as written along this line right here. So IR is along this line, and the value of current through this capacitor can be represented perpetually through this line right here. So I see I'm represented right here. So the resultant of these two phases will basically give us the value of I4. Now what we have to know is that now we have to find the effective voltage across this entire diagram, right? So what we have to know is that at balanced conditions, the value of the voltage across arm E2 plus the voltage across arm E4 is basically equals to the sum of voltage across E1 and sum of voltage across E3. That's why we have written E2 plus E4 is equal to sum of the value of voltage E1 plus E3. So this is the effective voltage across the Maxwell inductance capacitance bridge. So this resultant right here, this black line, is therefore the effective voltage across this bridge. Okay, so now we're going to look at some of the pros and cons of the quantum using this type of bridge. First pro of using this bridge is that balance equation, which is Z1 times Z4, which is equal to Z2 times Z3, is independent of frequency. Second advantage is that it is useful for measuring a wide range of inductances, power, and audio frequencies. Now, to look at some of the disadvantages, first thing, it is very costly to use a variable capacitor. As you can see, we have a variable capacitor right here. It is very expensive and sometimes costly to use it. So sometimes, in order to fix this disadvantage, fixed capacitor is used instead of a variable capacitor. Second disadvantage of this bridge is that it is limited in the measurement of low quality factor, meaning quality factor that is less than value of 10, which is not effective in measuring it. So yeah, it is limited in measurement of low factors. Okay, now we're going to solve some questions related to the Maxwell inductance capacitance bridge. As you can notice, this bridge is a little bit different compared to the bridge that we used in the earlier sessions, right? As you can notice, the unknown variables are in a different position now. What you have to know is that these unknown variables may not always be in the same arm. They may switch places, and in order to solve the questions, we need to remember one thing, one tip, that is, if you want to find the value of Rx, what you have to do is you have to multiply the two adjacent resistors. Let's say this is Rx, right? And the two adjacent resistors are R3 and R2, and now we have to divide that product by the resistor opposite to the unknown resistor. So let's say we want to find Rx, right? So Rx can be found using the formula. R2 times R3 divided by the resistor opposite to the unknown resistor, right, which is basically R1. So substituting the values, as you can see, R1 is 470 ohms, R2 is 5.1 kilo ohms, R3 is 100 kilo ohms. So substituting these values, R2 is divided by the value of R1, right, which is basically 470 ohms. So the answer we will get is approximately 1.09 kilo ohms. So this is the value of the unknown resistor. So in order to find the value of the unknown inductor, what we have to do is it's in a different position, right? So a helpful tip is that we have to again multiply the two adjacent resistors located next to the inductor, right? So we have to multiply R2 and R3. Now instead of dividing like we did for the unknown resistor, we have to multiply the value of the capacitor. So the value of Lx can be found using the formula Lx equals to the product of these two adjacent resistors, which is R2 and R3, multiply by the value of the capacitor C1. So substituting these individual values, what we will get is, let's see, capacitor values 0.01 microfarad. We have to convert it to farad. So when you find this answer, we will approximately get around 5.1 Henry. So this is the final solution for the unknown inductor. So in conclusion, what we have to remember is that the value of the resistor and the value of the inductor may not always be in the same arm. It may change position. So a helpful tip is that if we want to find the value of the unknown resistor, we just have to multiply the two adjacent resistors and divide it by the opposite resistor. In case of the unknown inductor, we have to just multiply the value of the two adjacent resistors multiplied by the value of the unknown given capacitor value. So that is how you find the value of Lx and value of Rx. Thank you.